Right. The fourth property a mineral has to have is an ordered internal structure. And we're going to spend a little while on this one because this one's pretty important. So an ordered internal structure means that the mineral is crystalline. Crystalline means that if you zoomed in and looked at the atomic organization of the mineral, the pattern is repeated, right? All of the angles are repeated. The pattern is repeated. The angles between each element, each bond, each compound are the same over and over and over again. So in this image, if you look down at crystalline SiO2, which we call quartz, you get that snowflake pattern that's repeated over and over and over again. Now, just because something is SiO2 does not mean it's crystalline. You can have amorphous SiO2, and we call this glass. And if you looked at the atomic level of glass, it's just kind of disorganized, chaotic. It's not repeated over and over. So crystalline SiO2 quartz is a mineral. Amorphous SiO2, which we call glass, is not a mineral. Now, thinking about how do these elements actually bond, right? What's creating these organized internal structures? That's what we're going to spend some time on here. There's lots of different ways that elements can bond to each other to make compounds. And it really comes down to how many electrons they have and how many electrons they have in their outermost shell, right? So when we think of an atom, it's got a nucleus, which has protons and neutrons. And orbiting that nucleus is its electrons. And electrons orbit in layers, kind of like an onion, right? There's these orbital shells. And the larger an element is, the more electrons it has, the more orbital shells it's going to have. Now, the electrons in the outermost shell we call valence electrons. And we have this octet rule, which says that in general, an atom is most stable, right, if there are 8 electrons in that outermost shell. So if it has 8 valence electrons, the atom is stable. Now, not all elements naturally have 8 valence electrons. So for example, silica has 4, magnesium has 2, sodium just has 1. So on their own, none of these elements are stable, right? So in order to become more stable, they're going to want to bond with another element, right? So let's have some examples of that. So sodium, Na, it only has 1 valence electron. So it's unstable and it's going to want to get rid of that valence electron so it can go down to the lower shell that does have 8. Right? On the other hand, chlorine, it's unstable because it has 7 valence electrons. So it's going to want to gain a valence electron to get 8. Right? You see where I'm going there? Sodium wants to lose 1, chlorine wants to gain 1. Maybe they're going to be a good pair, right? And then neon, it naturally has 8 valence electrons, so it's happy on its own. It's what we call a noble gas, super stable on its own. Okay. All right, so let's talk about how these atoms can start bonding with each other. Right? So I kind of teased it before. Sodium wants to lose an electron, chlorine wants to gain an electron so that they can both have 8 valence electrons on their outer shell. So that makes them super likely to bond. Right? Sodium will give up its electron, chlorine will take that one, and they'll bond to become sodium chloride, NaCl. And when that happens, when electrons are donated by one atom and accepted by another atom, we call that an ionic bond. Now, this isn't the only way atoms can bond. They can also bond by what we call a covalent bond. And this is when electrons are shared, right? So chlorine atom wants to take an electron. And it could pair with another chlorine atom that also wants to take an electron. And rather than swapping electrons, they're just going to share it, right? So each chlorine atom is going to keep all of its own atoms, but also share another chlorine electron, right? I think I misspoke. Each chlorine atom is going to keep all of its electrons plus share one of the other one's electrons. And this means that both technically have 8 electrons in their outermost shell, right? So chlorine can pair with itself, can bond with itself in a covalent bond. Neon can do the same thing, or nitrogen can do the same thing. All right, so this gets us to the generation of ions. Right, so whenever I talk about elements, I'm just talking about the element itself. When I talk about ion, I'm talking about an element that is charged, right? And that means that there's some imbalance of electrons and protons there, right? And this happens when an atom either gives up or receives an electron, right? If an atom gives up an electron, then it becomes overall positively charged, right? It loses a negative charge, so it becomes overall positively charged, and we call that a cation. If an atom gains an electron, it's becoming more negative. We call that an anion. So cation is positively charged, anion is negatively charged. Okay. So going back to our examples, all of these atoms will become positively charged. They'll become cations when they give up the electrons in their outermost shell. So silica is going to give up 4 valence electrons, become positively charged. Magnesium is going to give up 2. Sodium is going to give up 1. Right? So when I talk about ions, I'm talking about how they're overall charged, right? Now, we've gone through the typical bonding, but some types of materials bond in a special way. For example, metals. So when metal elements bond, so think like gold, silver, things like that, the electrons are just free to move through the crystal lattice, right? It's not like the electrons are stuck with one atom within a single orbital shell. They just kind of move around, right? They're free to roam around. So there's mobile valence electrons. And right, this is called a metallic bond. The next unique bond we can have is what we call van der Waals bonds. And this is super common in clay minerals. And there's no electrons needed here, right? Look, mom, no hands. Look, mom, no electrons, right? Instead of electrons doing the bonding, there's just a weak electrostatic charge that keeps these crystal structures together. And that's one of the reasons that clay minerals are so fragile. They're so easy to break apart. And it's because they don't have those strong chemical bonds. It's just those weak electronic charges, right? So clay is very susceptible to breaking apart. And that is all the ordered internal structure, right? So in order to have that ordered internal structure, these elements, these ions have to bond the same way with other elements and ions over and over and over again in the exact same shape in the exact same way.